Yeah.
You ready to go? Let me see if I can get the wireless mic to work. I think
I got
this
this one
announcements
and that one. Okay.
We pass it around.
There's also this one, I think, is.
Test. Okay, maybe we'll
Sounds like it's on.
test. Is it going?
Sounds like it.
Test. Okay. Everyone, we're going to get started in about 2 minutes. Can't hear me?
No, I can hear you now.
With the microphone or without?
With the microphone.
Okay. I was taught to make sure to speak into it straight. That's the best way to make it work. So we'll give it just a moment.
I'm glad you know the trick.
Yeah. Well, everybody's gathered, so we might as well go ahead and start. We're going to start about a minute early. I want to welcome everybody to the Naperville Astronomy Club meeting for February. Just a little bit of a preview of our meeting. Just want to call out, we're going to have a wonderful guest speaker, and then we just do a little bit of club business, and our general goal is to get everybody wrapped up and out of here by, say, 9 o'clock, like, as soon as we possibly can. We won't belabor anything in terms of our club execution. One thing I wanted to just call out, just as you think about your evening, informally, we always gather at Bottoms Up. I finally got that name right. Yep. I always forget that every month. We head over there. Everybody in the room is welcome. Grab a late dinner, grab a Coke, grab a beer, whatever you fancy, and just a way to gather and kind of create a little bit of fraternity in our club after our event. And it's totally an unofficial thing, but we do it every meeting. So there's that. And I'll remind you guys before we wrap. And with that, I'm going to turn it over to Bill Henry, and he's going to announce our speaker for the evening.
Okay.
Fantastic.
Okay, well, welcome everybody. Tonight we're going to talk about stars to scans, cosmic origins of medical imaging isotopes. So this is a change up from our standard fare. Can you guys hear me okay?
Yep.
Instead of our usual perspective looking upward, tonight we're going to be looking inward, specifically medical imaging. From the first medical x-ray 130 years ago to the latest in, I don't even know what this is, single photon and positron emission imaging. These technologies have their origins in astrophysical processes deep in space that have been replicated here on Earth. I guess reactors and accelerators. Tonight's presentation is going to explore this fascinating intersection of nuclear medicine and astrophysics. Our speaker is Dr. Wesley Gohn, a scientist at Siemens Healthineers, a global leader in medical imaging, where his research focuses on, no pun intended, single photon emission computed tomography. His work integrates his background in nuclear physics with advanced computing and data science. Previously, Wes did experimental physics at national laboratories, including Fermilab, where he worked on the muon G-2 experiment that was published, those findings, just last year in June. Also at the Paul Scherrer Institute in Switzerland and the Jefferson Lab in Virginia. Wes has a BS in physics from Indiana University and a PhD in physics from the University of Connecticut. And for the last 5 years, Wes has been a member in good standing of the Naperville Astronomical Association. So let's give it up for one of our own.
Okay. All right. Sounds like that's working. All right. So thanks everybody for coming. This talk's a lot of fun to put together. So I'm a nuclear physicist by training, but I'm going to intersperse a lot of astronomy and talked about medical imaging. So I get to talk about a lot of fun stuff that I don't usually get to talk about in my regular, day-to-day work. So this should be a lot of fun. I'm going to go through some, really basic stuff that you probably learned in school, but just to make sure, I'm going to use a lot of these terms throughout the talk, so I want to make sure that everybody remembers, what these things mean, especially, the basic definitions, between an element and an isotope. When we talk about an element, that is talking about how many protons the atom has. An isotope is the same element, so the protons don't change, but you can add neutrons, and that makes it to a different isotope. There are some stable isotopes and some that are radioactive. So we're going to talk a lot about radioactivity because that comes into both medical imaging and then also how a lot of these elements and isotopes are formed. Also, I want to remind you the half-life is just how long it would take for some radioactive isotope to decay half of its mass away. So that gives you kind of an idea of how long it'll live. So if you have some isotopes have half-lives of many, many billions of years, and they could have been created at the beginning of the universe, and they're still here. Other isotopes we'll create in a lab might have a half-life of 2 hours, and so we have to use it really fast or it all just kind of evaporates and decays away. So, I did want to make sure I got at least one good astronomy picture in the talk, so start there. So where do the elements come from? So I'm going to go through slides on all these, but hydrogen and helium and tiny little bit of lithium were made in the Big Bang. Then stars have nuclear fusion going on in their cores that build elements up to iron. Then there's some slow processes in really big old stars that can get past iron. I'm going to talk about that a little bit, but that's not a large percentage of the element creation. Then stellar explosions make a lot. So most of the stuff that is heavier than iron gets made in these stellar explosions, supernova, X-ray bursts, neutron star collisions. So this nice picture here from this is from the European Space Agency. This is Cassiopeia A, which is, I learned, the youngest known supernova remnant in the Milky Way. It's only 11,000 light years away, so we can get nice pictures of it. I'm not doing that with a mouse. Somebody else doing that? All right. And then there's some elements that don't actually get made in stars, but we have to make them in labs. But then I'll still talk about, the reagents that we use to make those elements still come from these nuclear processes in stars. So, just really quick, the Big Bang. Everybody's seen some version of this slide. I took this from Lawrence Berkeley Lab. They have a lot of nice graphics that are free to use, which are great. But in the first 3 to 20 minutes of the universe, we already had protons and neutrons, and they were starting to combine to make hydrogen nuclei and helium nuclei. And then soon after, they start pulling in electrons to make the full atoms. It took then, something like 100 million years later, we start getting stars, and then, all this other nuclear physics can start happening. So for the first 100 million years of the universe, after 3 minutes, it was just lots of hydrogen and helium. Again, just to define a term that we're going to use a lot, nuclear fusion. So this is kind of the battery that keeps stars burning. It's also, something we're trying to do in labs to, generate energy. The reason it's so good at that is that it's a really clean energy source. So it doesn't cause a lot of pollution, and there's not a lot of leftover radioactive material like with fission. So the way it works is two elements that are lighter will fuse together to create a heavier element. And since the difference in mass between the heavier element and those lighter elements is a positive number, then you get some energy output that you can harness to power a city or a star or whatever you want to do. So this is just using Einstein's famous E equals mc squared, taking that extra mass and turning that directly into energy. So how does this happen in stars? So we start with hydrogen. Hydrogen fuses to make helium, helium fuses to make carbon, and you get this whole chain. So you end up with sort of an onion structure inside of your star, where at the core, you'll have a hot iron core, and then each layer outwards is a lighter element. So you can't go heavier than iron, because when you pass iron, then this curve starts going back up the other way. So instead of releasing energy, if you try to fuse two iron atoms or nuclei, then you're going to actually have to put energy into that. So the reaction turns around the other way. So it can't happen in a star. And I mean, if we wanted to do it in a lab or something, we'd have to pour a bunch of extra energy in. So it wouldn't be a good way to generate energy either. There is, I alluded to earlier, a slow neutron capture process. So this only happens, so this doesn't happen in the sun, but in really old, really big stars, we call it so AGB stars, there's this process where the iron nuclei can just slowly sort of accumulate neutrons, and then they grow. So you can get, via these neutron capture processes, you're able to get heavier elements. So they capture a neutron. Once it gets too heavy for that to be stable, it'll have it undergo a radioactive decay. One of the neutrons turns into a proton, and you get another element. So you can get, so the iron can go up to nickel, to all the way up to lutetium and beyond. Supernova have a very similar process. So the S process is this slow neutron capture. When a supernova happens, we have something called the R process, which is a fast neutron capture. It's almost the same physics, except that instead of something slow that happens over millions of years, it's a fast process that happens over seconds. And the only difference really from a nuclear physics standpoint is in the S process, the iron is capturing 3 neutrons at a time. In the R process, it's capturing 5 neutrons at a time. It's a lot more energetic. Things are bouncing around. The star explodes. So it's a whole big thing. And this is just a little animation kind of show. So this chart, I'm going to show a lot. And so on the vertical axis, the number of protons. The horizontal axis is the number of neutrons. And see, as the supernova progresses, then the distribution of what elements are present inside the star kind of shoots up this curve, which populates this R process. And I'll show you a little bit more details and explain more what this means in a minute. But another process is X-ray bursts. So these happen on the surface of neutron stars. In particular, when the neutron star is in a binary system with another star, and it'll suck material off of the other star, and it kind of makes a crust around the neutron star that gets really, really hot. When it gets hot enough and there's enough gravity pulling on it, it'll start to undergo its own nuclear fusion just in that crust. And it has a process called the rapid proton capture process. So this is really just a thermonuclear explosion happening on the surface of a neutron star all around the star. And we can detect these as what we see as X-ray bursts when we see these in the universe. This is one of the few things from the nuclear physics side. I worked on this like 20 years ago at Michigan State. We were doing this all theoretically, but the astronomers would give us observations of these X-ray bursts. They do a lot of spectroscopy to see what elements are there. And then we're running a nuclear physics simulation to try to match what happens in the RP process to the final abundances of elements that are left over. So I got to work with this old Fortran code, which was old even 20 years ago. And to make it worse, all the comments in the code and the variable names were in German. So it was, for a young undergrad, it was, I guess, par for the course. But it was a fun project to learn more about how this stuff happens. There's also been a lot, we've learned a lot recently about neutron star collisions. This is some publication from the Webb telescope from just 3 years ago, a little less than 3 years ago. They've seen that there's a lot of heavy elements produced in neutron star collisions. More than, I mean, we used to think the heavier elements were pretty much all supernova. And we've been learning lately that a lot more of them are coming from neutron stars. So you still get, I mean, supernovas still produce a lot, but in terms of the abundances we see in the universe, the collisions of neutron stars are creating a lot more. I was going to add a picture, and I forgot. I actually I gave a seminar at Goddard before Webb launched. Actually, I got to see Webb in they have a giant clean room. I think they said it's the biggest clean room in the world. And it was all folded up with the big gold thing on top. Like, it was cool. But now it was maybe a year before they launched it, 2 years maybe. But there's been a lot of good science coming out of this in the last couple of years that I'm sure a lot of you have followed and closer than I have. So to put kind of all that together, this is that same chart. So again, so I have the number of protons on the vertical axis, the number of neutrons on the horizontal axis, and you can see kind of all these different processes I talked about. So the Big Bang makes the really light stuff. This RP process is making elements up here. The S process is kind of in the middle. And then this R process is going down here, and that gets a lot higher. So that's happening in the supernova and things like that. So you can see that by combining all these different effects, we're able to sort of populate all of these elements and isotopes that we've observed in the universe. And then how do they get to Earth? So supernovas explode. There's clouds of dust that have all of these elements floating around. Eventually a new solar system forms. All the dust gets packed into planets. We got lucky enough to be on one of these rocky planets that had lots of dust. For many millions of years, it's liquid soups, right? So if you think about the experiment you do when you're a kid, where you layer lots of different densities of liquid and mix it up and leave it overnight, you come back and there's layers, so they all separate. Same thing happened on Earth when it was a big ball of soup. But when it separated, then we get veins of iodine ore, gold ore, uranium, all the other stuff. That's how it ends up, all in one place. There's also, as I mentioned, some isotopes we're not able to find in nature at all. Most of these were created in stars, but their half-lives are too short. So they're not around long enough to get formed into a planet. So we have to make them ourselves. So there's essentially two big ways we do that, either with particle accelerators. These two pictures on the left, the diagram and the photo, are cyclotrons. A cyclotron just is essentially a great big magnet and has a rotational magnetic field. So you inject charged particles, and it makes them kind of swirl around. Every time they go around in a circle, they get faster. And then we can smack those into a target so essentially inject protons into the cyclotron, smack them into a target, and then you're able to build up elements that way. The other way is in a nuclear reactor. You do almost the same thing, but with neutrons. You have a target, you bombard it with neutrons, it'll capture some of them, and then build up into heavier elements. Again, so going back, I've mentioned radioactive decays a couple of times, so just to remind everybody, because this will matter more once I start talking about the medical imaging side. There's essentially 4 types of radioactive decay that we'll talk about. For imaging, mainly worried about the gamma emission and the positron emission. So back when like Rutherford was studying this stuff it was in 1899, he saw 3 types of particles decay. He called them alpha, beta, and gamma. He was able to separate them because he I think he was using uranium, put it in a magnetic field, and he saw some of them got bent this way, some got bent this way, some of them weren't affected. So if you put a charged particle in a magnetic field, depending on if it's positive or negative, it'll bend it one way or the other. So he surmised that some of these particles were negative, he called them betas, some were positive, he called them alphas. He didn't know what they were. And then later they discovered the gammas. We learned later that once we measured their mass and things, that the gamma rays are just photons, the beta rays are electrons, the alpha rays are actually a whole helium nucleus. But the name stuck. So even though we know what they're called, still everybody calls them gammas and betas and alphas. There's also positron emission, which is a lot less common, but mentioned it because we're going to talk about it for PET imaging. That's where the nucleus gives off a positron. The positron, since it's an antiparticle, will kind of grab onto an electron pretty quickly. The positron and the electron annihilate, so when an antimatter particle and a regular particle meet each other, they essentially just evaporate into pure energy, which means it gives off 2 photons. And both photons are traveling in exactly opposite directions at exactly energy of 511 keV, which is the mass of the electron. Okay, so to the medical imaging part of this. So there's 2 types of medical imaging I'm going to talk about that use these nuclear processes. There's SPECT, which is single photon emission tomography. It's the machine on the left. And PET is positron emission tomography. It's the machine on the right. I forgot to say at the beginning, feel free to stop and ask questions whenever you want, in case anybody was waiting to ask a question. I'm happy to take them anytime. So I work on SPECT, but the company I work for builds both of these. So we have a factory up in Hoffman Estates where every SPECT or PET machine we sell anywhere in the world gets built in this factory up the road, right up 59. So I get to see both of these all the time. So the way SPECT works is you're detecting a single photon. So that's why the SP, single photon imaging. So we use 2 gamma cameras, have one on either side of the person, and they kind of move around. And then we put a big lead collimator in between the person and the detectors so that we can tell the direction that the photons are coming from. Since we just get 1 photon at a time, that's the only way we can really tell the direction. And we use 2 detectors at once so we can triangulate. So if we're getting hits in both of these, then we're able to kind of triangulate where in the person's body the radiation is coming from. So I should have mentioned that. So in both of these modalities, the patient's injected with some radioactive material. So it's different than you probably used to seeing CT scans or X-rays. They use radiation too, but there's a gun, like a radiation gun outside, and they pass the radiation through the patient and then detect it on the opposite side of the gun. In this, the radiation's inside the patient. So it's very good for imaging soft tissue, essentially anywhere blood goes, where like X-rays are better for bones and things. So you can see it's just an image, just an example on the right where this is an image from lutetium therapy, where over 3 days you can kind of see as the lutetium decays away. So the way this works, so we have the gamma rays pass through a collimator. Then we have some kind of photon detector, usually photomultiplier tubes, but it doesn't have to be. I talked a little bit about different kinds of detectors we can use. Then a computer that takes all these signals from the photomultiplier tubes and creates a display. There's different kinds of collimators depending on what we're trying to image. Sometimes people use pinhole collimators, which work just like a pinhole camera, but they're thick lead, so it works for gamma rays. We use a lot of parallel hole collimators. Sometimes people design fancier collimators to try to look for, might be specialized to look at your heart or your brain or something like that. But it's all the same basic principles that you use in imaging, you know, for instance, in a telescope. Just a little bit about, you know, why the collimation matters. So essentially, you want to tune the collimation to maximize both the sensitivity and resolution. So by making it harder for the gammas to get through, then you get better imaging resolution, but you're losing photons, so you're going to lose sensitivity. So you got to try to balance that. All right, so PET imaging works similarly. The patient's still injected with a radioactive substance, but it's something that decays into the positrons. And the positrons, as I mentioned before, will then decay into 2 gamma rays, and you have to detect both gamma rays. But the good thing about this is that since you're detecting 2 gamma rays that you know are coming from the same point, and you detect them in coincidence, then you know exactly where they came from, right? So with SPECT, you're just detecting single photons, and then you try to use kind of a triangulation, and it's sort of a statistical process to figure out kind of where the photon came from. With PET, you know exactly where it came from, as long as you can measure the time coincidence precisely enough. So it all comes down to the better precision you can measure the timing, the better precision you have in your resolution of the patient. Now, there's challenges with PET. I mean, some people might say, well, why don't you just always use PET? I mean, it generally gives a better image. But there's some things that it can't do that well, which I'll talk about a little bit. But also, it's a lot harder to get these isotopes. So the nice thing about SPECT is you can use essentially any isotope that gives off gamma rays. You can use that for imaging. With PET, you can only use these certain isotopes that give off the positrons. And they usually have very low half-lives. So essentially, for a hospital to have a PET machine, it has to be within, you know, a 20-minute drive of a cyclotron that can generate these isotopes. A lot of the SPECT isotopes live for weeks or longer, right? You don't want it to live too long because you inject a person with radiation, then they're walking around with radiation. But you want them, you know, ideally within a week or so to decay away and be non-radioactive. But with the PET isotopes, it's usually you have a couple of hours after the isotope is produced to eject the patient, do the scan, and then it's totally decayed away. So the way this works is, since it would be too slow to do, like with SPECT, we have the 2 big cameras that kind of slowly move around. With PET, we just surround the patient with cameras. And you have to detect 2 photons at the same time with really, really good timing. And then you can make these really nice high-resolution images. So to compare them a little bit, you can see, so the top 2 lines here are just comparing the SPECT on top to the PET on the bottom. They're both relying on radiation in the body. It's good for both of them are good for organ function, things that move around in the body. You can trace blood flow, you can trace digestion, things like that. I read while I was researching this, that you can detect early stage cancers 6 months earlier than you can with just CT, or MRI, or X-ray, just because it's really imaging the tissues in the body more than those other modalities are. But like I mentioned, since SPECT image from just one photon and PET uses 2, you get much better resolution from PET, but since the SPECT isotopes have longer half-lives and we can manufacture them easier, then more hospitals are able to have SPECT systems than PET. So you get into a lot more rural areas, third world countries and things like that, where they don't have the infrastructure to make PET systems, they can still have a SPECT. Essentially, the business model of the companies that are not our company, but companies that make these isotopes, the people who make isotopes for SPECT, essentially they'll have one factory somewhere in the world that makes, has a cyclotron or whatever, or a nuclear reactor, and they're making these isotopes. Then they can overnight ship that to any hospital in the world, essentially just with FedEx or UPS or whatever, and it can get there in time. Now with the PET, the supply chain's a lot harder. It's usually like big cities because you have to essentially make the isotope, put it in a car, drive to the hospital, and use it. Right? A little bit more about detector materials. So I'm going to start getting into, for the rest of the talk, talking really about the elements that we use for the medical imaging and where those came from. I'll try to connect at the beginning of the talk. So right now our Siemens SPECT systems use sodium iodide detectors. So the sodium and iodine are, sodium was made in massive stars, it's just a carbon and neon fusion. Iodine is made in supernova and neutron star mergers using the R process, the neutron capture I talked about. Our PET systems use silicon detectors, which were also made in massive stars, just fusing oxygen and then silicon burning. There's also some newer SPECT systems that use something called CZT, which is an alloy of cadmium, zinc, and tellurium. CZT is a lot easier to say. So this is from a company that produces these detectors, Chromac. Took a couple pictures from them. So the zinc is made in massive stars and supernova. The cadmium is made in the AGB stars, that's S process in these really old stars, and also some in stellar explosions, and the R process, and the tellurium is made only in neutron star mergers. So this is just common isotopes used in medical imaging until I used ChatGPT to make this, because it's great with pictures, but it makes the words all funky. But if you just ignore when it can't type, then it's okay to read it. So on SPECT, we use mostly technetium-99, and then for specialized procedures, we use a lot of iodine for thyroids, and then we also do lutetium and actinium. In PET, it's mostly fluorine-18. Then they use some carbon-11, nitrogen-13, and oxygen-15. So technetium-99. So this is what we use most of the time in SPECT imaging. So in our lab, this is what we're doing this like every day. Now, so Tech-99 has a half-life of a little over 200,000 years. So that is very short in timescales of the universe. It's created in supernova, but it's all gone now. So we have to make it from scratch. We make something called technetium-99M, which is a metastable state that has a much shorter half-life. So the half-life's on the order of days instead of years. There are hundreds of thousands of years. To do this, we use reactor fission. So you have molybdenum-99 created from uranium-235, and then that beta decays down to the Tc-99m. Interestingly, so technetium was the first element discovered that does not exist naturally on Earth, and it's also by far the most deployed isotope in medical imaging. So but since we make this from uranium-235, where did that come from, right? So that was produced via the R process and neutron star mergers. So even though we have to make all the Tet-99M ourselves, it did originally come from these nuclear processes in stellar collisions. Okay, iodine. So we use some different isotopes of iodine here. I wrote iodine 131 because that's what we use the most. But iodine's really great for thyroid imaging, mainly because the body kind of naturally puts all the iodine into your thyroid. And since it is radioactive, we can, after you're injected with iodine, we can just put you in a SPECT system and then we can see your thyroid. So it's used also for therapy, right? So even if we weren't imaging it, they would inject people with thyroid cancer with iodine because it kind of goes to the thyroid and the radiation burns the cancer out. But we're able to image it at the same time so you can see that that's working. So it's kind of doubly useful. We also sometimes use I-123, which is more just for the imaging side. And it forms in neutron capture nucleosynthesis, so primarily via the R process, but it's not radioactive, and so we can't use the inert iodine for medical imaging. We have to make it in a lab and then use the isotopes that we made in reactors or accelerators.
Does this mean the
Yeah.
T3, T4 test?
I don't know.
We
I
have
forget.
radioactive iodine in T3 or T4 test for thyroid?
I'm not sure. I work in the lab. I don't know what happens when it gets to people. All right, lutetium. So I know this is something that came up in the, a couple of months ago. We had another speaker talking a lot about some of this nucleosynthesis stuff, and the questions came up about lutetium. This is really an emerging medical imaging use case that's really been coming up in the last couple of years. I started seeing commercials for it on TV, maybe in the last year or so. But we can use this lutetium-177. It's called theranostics because it does both the diagnostic and the therapies, right? So the lutetium-177 is injected in a way that it'll go to the tumor or whatever, and it'll both help to treat the tumor, and then we can also use it for imaging the tumor. It's created, so stable lutetium is created in the S process in these really old stars, and then like iodine, we can then pump it full of neutrons in a reactor process to make the radioactive isotope lutetium-177. The half-life of that's about 6.6 days. So this is one of those things I've talked about where they'll make it in a reactor and then literally send it in the mail overnight to the hospital. Yes?
You finally got to my question.
Good.
I have had 2 PET scans.
Okay.
I had prostate cancer about 6 years ago,
Yep.
and in checking to see if the hormone treatment had worked properly, I got a PET scan basically from mid-body south to
All right.
about the knees. As it turns out, my prostate cancer was essentially gone, okay? However, they also picked up some glowing areas in my lungs because some of the prostate had migrated or
Sure.
metastasized, pick which word you like, to my lungs, and there were nodules there. So they treated that with higher dose radiation, and to make sure they got all of that, I got the second PET scan, and I was clean of all of the cancer. Here's my question. What is it about magical lutetium that is attracted to cancer cells and leaves normal cells alone?
Right. So that is actually more of a chemistry question than a physics question, but and I'm sure there's physicians who could answer this a lot better than I could, but in general, I can say the way it works is they use some other substance that binds to the lutetium that is attracted to the cancer cells. So there's essentially they're pulling it in by some chemistry in the body that so they know if they inject you with this other substance that will get concentrated in your cells, especially in the cancer cells, and so they essentially mix that with the lutetium. Those kind of bind together, and then the other substance pulls the lutetium into the cancer cells. Yes.
So I too
Yeah.
had hello? I too had a scan, and I inquired to the doctors what was going on, and they said they use glucose that attaches to the lutetium, and it's because cancer cells grow fast, and they have a higher metabolic rate, so they naturally absorb that glucose preferentially, and that's what causes the tumors to grow.
Did you get a warning from the doctor that while you have that, it's a short half-life, 6.5 days,
Yeah.
but while it's decaying, stay away from your wife.
Yeah.
I'm serious, for 2 weeks, try to keep a distance from your wife. Don't bring your dogs close to you or anyone else, because you are radioactive for
Yeah.
about 2 weeks. And after that time, then the half-life has killed it down to where it doesn't matter much.
Yeah, a lot of hospitals will have you stay in a hotel by yourself for a couple of days
Yeah.
after these treatments. Yeah. Yes.
We have a housekeeper who has had cancer, and
Mhm.
she's had nodules. She's had nodules that have been shrinking and then growing again. And she was told to stay away from sugar because sugar nourishes cancer cells.
Right. That. Yeah, I'm not a physician, but that sounds like that is right in line with what Bill is saying. Yeah.
All right, so you've been mentioning some of these isotopes are made in nuclear reactors. Now,
Yes.
all of us are nuclear engineers, and I did get involved in a program to make cobalt-60 reactors.
Sure.
Are these research reactors? Normally full-size reactors, we don't take stuff out.
Oh, sure. Yeah. I mean, they're not just like, it's not just a byproduct from like a power plant. They have, the companies that make these have, a dedicated reactor that they're using where they're essentially making like a neutron gun. And then they have a target with whatever they want to irradiate, bombard it with neutrons to capture neutrons and build up to another isotope that's radioactive.
Small specific.
Yeah, yeah. Yes.
What kind of resolution do you get with the various modalities? In other
Sure.
words, how small a thing is being resolved?
Yeah, it depends a lot on, there's a pretty big variation between the different modalities and then also, the different types of therapy. But in general, the best resolutions are like a couple of millimeters. So it's not nearly as good a resolution as, so CT can have a lot better resolution, but the problem is depending on what you're looking at, sometimes the cancer cell, the CT can't tell the difference between a cancer cell and a fatty cell, right? And this can. So there are things where this gives you more advantages over the resolution.
Can I ask a cost
Sure.
question?
Sure.
Let's say a country in Europe wants to borrow one of your PET scan machines. You ship it over there. What's the charge? How much does it cost to do that?
I don't know like exact numbers, but the range is on the low end machines probably $500,000, highest end machines 10 million.
I only asked that because twice I've been charged for a PET scan and they were $7,000 each.
Yeah. Yeah, they're
This
expensive.
must be the most expensive machine in the universe to charge
Yeah.
that. You're in it for literally for seconds.
I don't want to get into health insurance, but I mean, I will say that we charge the same for PET machines in America and in Europe, and the hospitals don't charge the same.
Yeah.
From what you're saying, it's not just the machine, it's the cost of what they inject into it.
Sure, yeah, I mean, but that's, I think, a small, I mean, it's not cheap, but compared to the cost of the machine, it's not very expensive.
It's too bad, one of our members actually used to inject that radioactive stuff into people for PET machines,
Oh, yeah,
but he's not here tonight.
okay. Yes,
So, in terms of the shipments of these materials that are created in your reactors, like what quantities are being sent to like individual, like when you have one of these devices?
Sure.
How much is actually being used in those situations?
I think it's gonna depend a lot on the specific use case.
Okay.
And I mean, I don't have a good quantitative number for that, but I've seen like essentially it's, you know, a vial about this big. And depending on what, you know, what the treatment is, it could be more or less. But,
And
yeah.
is that vial, is that
Yeah.
all of the material that was created in the reactor, or is that?
I mean,
also-
it's mostly,
Yeah.
I mean, the vial's mostly water, right? But it's, and then depending on what they need, you know, how much radiation they need in the patient for that particular use case, they mix more or less of the radioactive substance in.
So we're talking like a few grams.
Yeah, right. All right, so I do have a couple more of these similar slides, similar treatments. Actinium-225 is actually used for very similar applications. Hopefully, none of you need actinium-225 scans, but if you, I'm not sure, as far as I know, this isn't even FDA cleared yet, but it's something that's happening a lot in labs. But 10 years from now, there's a good chance that if you had prostate cancer, they'd use actinium-225 instead of lutetium. And a big reason for that is that they can use something called targeted alpha therapy. So actinium decays in alpha particles, and those alpha particles are very efficient at burning out cancer cells, but they travel a very, very tiny distance in the body compared to lutetium gives off beta rays, which are electrons. And so you're getting, instead of an electron, you're getting essentially 4 big nucleons pounding into your cancer cells. But to accomplish that, they do this targeted alpha therapy where they have to image you, figure out exactly where the tumor is, and then they will inject the radioactive substance directly into the tumor. So compared to pretty much all of these other things, they'll just inject it into your arm and then it flows through your bloodstream. But with these alpha emitters, and there's others, actinium's probably the most promising right now, but there's others like that they're looking at, thorium, things like that. But I don't want to bring actinium up. It's a 10-day half-life, so not too much longer than lutetium. And there's 2 routes we can use to make it in a lab. You can make it either in a particle accelerator or in a decay chain from a reactor, but both use thorium. So we already talked about uranium. So talk about thorium-232. So this was formed in our process and neutron star mergers. Has a half-life of 14 billion years. So thorium-232 that was formed in the first stars in the universe is still here. And so we're able to go mine this and then use it to create things like actinium-225. So PET isotopes. So PET uses a lot lighter isotopes that are usually better for these positron emissions. And so I'm just talking about a little bit about fluorine. Fluorine-18, it's produced in cyclotrons, has a very short half-life. And so to create it, they fire protons at enriched water, transforms the oxygen into a radioactive fluorine isotope that they can then use for PET imaging. And you get these very clear images like you see here on the right. All right, so this is my last slide. So that was, all right, pretty good time, I think. All right, so just to summarize, so this is a nice periodic table that is broken down by color with kind of everything I talked about. So the Big Bang stuff is in red, so you see the hydrogen and helium. Below that, the purples, things that were made in cosmic ray-induced fission, which I didn't talk about, but there's only a couple elements and we don't use those very much, so skip those. Then the dying red giant stars, those AGB stars I talked about, are the materials in green. The blue, kind of lower down, are coming from neutron star collisions. The kind of the white dwarf supernova are kind of that fourth row, and then all the brown stuff down at the bottom is artificial synthesis. Oh yeah, and the giant star supernova are in the same region. So you can kind of see as you get further down, you're getting more into neutron stars or the artificial stuff, and the lighter elements up at the top are more supernova or dying stars, that sort of thing. And then just a few more images and some use cases. I don't have time to go through a lot of the use cases, but we do a lot of brain imaging with both SPECT and PET. You can use both these, especially to have like early diagnosis of Alzheimer's just by imaging amyloid content in the brain. We use both for cardiology, especially with both of these. They're nice because you can see kind of how the blood is pumped through the heart, because you're really imaging the blood in the heart more than just, if you can do a CT scan and see the heart, but with these modalities you can actually watch the blood get pumped through, so you can see earlier perfusion and how the blood's flowing through the heart. We talked about oncology. It's very good for diagnosing tumors. And then there's other less prevalent things like infection and orthopedics, endocrine. I've seen some SPECT diagnoses of the digestive system where they actually make a patient eat radioactive material and then sit in a SPECT machine, and then they can see it go through their digestive tract. But yeah, that's everything. So, all right, so thank you all for letting me talk, and happy to take more questions.
Let's hope you never need one of the machines you build.
Oh yeah, and same goes for all of you.
So I have a question.
Sure.
So if one of us should happen to need one of these scans,
Sure.
Can you get NAA members a discount?
No. I wish we're not even, the FDA won't even let us, like I can't even scan myself. It's illegal. Yeah.
So I just have a question. I know you can use particles like they did first with the Surveyor spacecraft on the moon to bounce alpha particles off the surface to analyze what it was made of. So you could use it in geology, right?
Okay.
These types of technologies too. I guess there would be similarities where you're just shooting particles and analyzing what comes back.
Yeah, probably. So interesting, I mean, when I talk about the alpha therapies, and so the alphas travel such a small distance through the human body because they're so big that we don't really see any alphas coming out. So the actinium gives off the alphas that are used to treat the patient, but it's also giving off gamma rays at the same time, and we detect the gamma rays. So I don't know if they do something similar or not, but that's interesting to think about.
I was thinking Jim's kind of sponsored tonight's event indirectly.
Sure.
Do we have more questions for Wes?
Yeah.
We have the mic.
Okay, I might have missed this because I came in a little late, but how many machines per year does the company produce?
Oh, that's a good question. I should know that number, but I mean, it's probably around 1,000 of each SPECT and PET machines that get, and like I said, I mean, those machines get sold all around the world. I mean, plus or minus a few hundred either way, but something like that.
That's pretty impressive. And they all come out of Huffman?
Yep, yeah.
All right. Thank you.
More questions for Wes? All right, Holden.
If I had a chance, I'd go even further back. That's pretty funny. Wes, talk about the pinhole projection to get the imaging. I was just wondering, I was thinking about how a lot of us do our astrophotography and we do our, spectroscopy, or at least if you got into that kind of, what's the camera for the imaging? Is it just a simple chip camera, or is it more complex as well?
It's probably even simpler. It's just any photon detector. So for the SPECT systems we sell, it's all just a sodium iodide crystal with a photomultiplier tube behind it. So the gamma ray hit the crystal and make a shower of light that we detect in the photomultiplier tube. But then there's other types of detection. So you could use a silicon photomultiplier or a CZT crystal to do kind of the same thing. Yes.
Gadolinium?
Yes, that's. I know. I'm not personally, but I know that people are doing research on that. Yes.
So I was wondering, like my photomultiplier tube, do you mean like a vacuum tube or is it?
No, it's similar. So it's essentially, it creates an electrical cascade. So it's based on photoelectric effect. When a photon hits it, it generates an electrical signal. So it's essentially a way to take light from in one side and then create an electric pulse out the other side. And then you can calibrate it to know, roughly based on how big that pulse is, how many photons hit the tube.
Yeah. Okay.
Anyone else? All right, the NAA's own Wes Gohn.
All right.
Thank you.
Thank you.